Welcome to the Force Glider video. In exercise 1, we'll be calibrating the photogate phase offset and constructing amplitude and phase spectra for a glider undergoing forced harmonic motion.
Mount the linear driver on a stand and attach it to a spring. Attach the other end of the spring to a glider with a flag on it. Use an additional spring to attach the other end of the glider to a stand. Also, mount a motion sensor on a stand such that it is at least 15 centimeters away from the flag.
Plug the motion sensor into the digital ports 1 and 2, with yellow in port 1. Plug the photogate into digital port 3. Plug the power amplifier into the analog port A, and plug the red and black banana plugs for the linear driver into the power amplifier.
If you use a photogate that is mounted to the linear driver, note that you will need to find the phase offset between the photogate and the glider and subtract it from all of your measurements. Alternatively, you may use a separate stand and place the photogate such that the phase offset is 0 at low frequencies. Ensure that the photogate is triggered only once per cycle.
The purpose of this lab is to observe phase and amplitude behavior both below and above resonance, so you will need to adjust two parameters until the resonant frequency is near the middle of your range. You can add mass to the glider, but be careful not to cause too much friction. You can also lower the spring constant. Note that multiple springs in series will lower the effective constant.
Open Data Studio and click Create Experiment. Click port 1 and select Motion Sensor. Click port 3 and select Photogate. Click port A and select Power Amplifier. Click the motion sensor icon and change the sample rate to 25 Hz.
In the signal generator window, change the output to DC voltage. Double-click Graph and select Position to create a position versus time graph. In the setup window, click the photogate icon and click the state box. This will cause the photogate state to be shown in the data column. Drag it into the graph so that the position and photogate state are locked to the same time axis.
To ensure that your resonance frequency is reasonable, set the power amplifier to about 2 volts and press Start. Collect a few seconds of data, raise the power amplifier output by 0.5 volts, and repeat as far as possible until you hit 10 volts. As you approach resonance, you should see the amplitude increase with each step. If you have correctly adjusted your mass and spring constant, you will reach and pass resonance, at which point successive steps will cause the amplitude to decrease. If your graph does not decrease, you need to readjust your mass and/or spring constant. Note also that you can adjust the air pressure, either A, to minimize friction with large masses, or B, to increase the damping, which will in turn keep the amplitude manageable at resonance.
Turn off the driver and ensure that you still have an under-damped system. Press Start, set the system in motion, and record the damped oscillations.
Next, we'll construct our amplitude and phase spectra. Start at a reasonably low voltage and record data until the system has stabilized. Incrementally increase the voltage and repeat. Note that you should have a higher density of measurements near the resonance point because it's a nonlinear curve. Once finished, perform a second trial going from high voltage to low voltage.
In exercise 2, we'll be using Hooke's law and a force sensor and motion sensor to determine the spring constant K.
Hang the force sensor from a stand and attach it to the analog port on your data acquisition interface.
Hang a known mass from the sensor.
Open Data Studio and select Create Experiment. Click the first analog jack and select Force Sensor. Set the sample rate to 250 Hz and the sensitivity to medium. Click Calibrate Sensors, and in the 0.1 section, enter the force in newtons that your known mass is exerting on the sensor. Click Read from Sensor.
Replace the mass hanging from the sensor with a second known mass.
In the 0.2 section, enter the force this mass exerts on the sensor, and click Read from Sensor and OK.
Set up a stand at one end of the track. Arrange the force sensor and motion sensor as shown. Plug the motion sensor into the data acquisition interface with the yellow plug in port 1.
In Data Studio, click Setup, click the first digital port, and select Motion Sensor. Change the sample rate to 25 Hz. Create a graph of force versus position. Tape a flag to the glider and attach it to the force sensor with a spring. Press tear on the force sensor, press start in Data Studio, pull the glider back, and press stop.
Does light have mass? Of course not, it's not even Catholic.